Hi everybody. Today I want to talk to you about Kepler's laws to finish off our chapter on circular motion and gravitation. Now, Johannes Kepler was a German astronomer who lived from 1571 to 1630. He's best known for developing these three laws of planetary observation, and these are based on the observations of Tycho Brahe. It's important to note that Kepler preceded Newton, so Kepler's laws served as both inspiration and confirmation of Newton's laws of universal gravitation. Newton then re-derived Kepler's laws, as we'll see later, using his laws of universal gravitation, showing that his theory really worked. So let's go over some of Kepler's laws. The first one is that the orbit of each planet is an ellipse, and the sun is at one focus of that ellipse. So it might be worth it to review some of the geometry behind an ellipse. You might remember that an ellipse is the shape that if you take, say, two thumbtacks and you stick them in a piece of cardboard, right? And then you tie a string around the ends, take a longer string and tie one end of the string to one thumbtack and one end of the string to the other thumbtack. And then you get a pen and you trace at the far extent of where the string will let you around, then that's the shape you get. You get an ellipse. So we're going to define the foci of the ellipse as where you put the thumbtacks, and they're labeled on this diagram as F1 and F2. So they're located a distance c from where the dead center of the ellipse is. If you draw crosshairs between the short axis, which is called the semi-minor axis or the minor axis, and then the long axis or the major axis of the ellipse. So the crosshairs are at dead center and the foci are at a distance c along the long axis away from the center, right? Now, as you can see here, our string would be tied to focus 1 and focus 2, and then however long that string is to reach the edge of the circle, that would be R1 and plus R2 as shown in the diagram, all right? And the sum of R1 and R2 remains constant, which is why the idea of the thumbtacks in the string would work for drawing out an ellipse. So we're going to define the longest distance through the center of the ellipse as the major axis, and half of that is the semi-major axis, which is labeled S here. It's similar to a radius, but for the long axis of the ellipse. Speaking of similar to radius, the semi-minor axis is labeled in this figure as B, and it's the shortest distance through the center. So if you take the center and connect it to the short edge, halfway across is the semi-minor axis. Okay, so it's kind of like the radius, but for the short side. The eccentricity of an ellipse is usually called E, and it's defined as the ratio of the distance C divided by S. Remember, C is the distance along the long axis from dead center to the focus, and S is the semi-major axis. Now for a circle, since C sits at the very center, C is equal to 0, and that means the eccentricity is also 0 because it's C divided by S. The range of values for eccentricities for an ellipse is a number that's always in between 0 and 1. And the higher the value of your eccentricity, the longer and thinner your ellipse gets. And the closer it gets to 0, the closer your ellipse is to a circle. Now the sun is that one focus of that circle, or of that ellipse, and nothing is located at the other focus. Aphelion is the point farthest away from the sun, and perihelion is the point nearest to the sun. Aphelion occurs at a distance of S plus C, and perihelion occurs at a distance of S minus C. Okay, Kepler's first law. A circular orbit is a special case of a general elliptical orbit. Most planets, as we'll see, have orbits that are very close to circular. Elliptical orbits are more for planets like Mercury. It has the highest eccentricity of any of the planets. Elliptical and circular orbits are allowed for bound objects. So since the planets continue to go in an orbit around the sun, they're considered bound to the sun and part of that system. An unbound object would pass by and not return. There's some comets that do this. Like I was saying, Mercury has the highest eccentricity of any planet. Its eccentricity is about 0.21. In this table here, I list the planetary orbit eccentricities for other things. The Earth's eccentricity is 0.0167. So remember, the closer it is to 0, the closer it is to a circle. So you can see that Earth's orbit around the Sun is basically circular. Okay, enough about the first law. Kepler's second law says that an imaginary line drawn from each planet to the Sun sweeps out equal areas in equal times. So here in the cartoon, we can see a green planet, for example, in orbit about the Sun. Remember that the orbit is an ellipse with the Sun at one focus and nothing at the other focus. So you can see here that when the planet gets close to the Sun, say on path 1 to 2, it sweeps out a longer distance in the same amount of time, right, compared to its furthest away from the Sun, indicated here in 3 to 4, where the amount of path that it sweeps out isn't very long for that same amount of time. And this is because it has to sweep out equal areas, right? So as it gets close to the Sun, the distance between the planet and the Sun is shorter, and that means that in order to sweep about the same amount of area, it has to pass through a longer arc, right, in order to get the same area as a point that's further away from the Sun. The consequence for this is that in order for this to happen, the speed of the planet has to change as it travels around the Sun. Since the path from 1 to 2 is longer than the path from 3 to 4, but the time is the same, the planet is faster near the Sun in its orbit than it is when it's further away, and it travels slower. All right? This is actually a consequence of the conservation of angular momentum, which we haven't covered yet. So when we talk about angular momentum, maybe we'll revisit this idea so that you can understand it a little bit better. But for now, let's talk about Kepler's third law. Kepler's third law says that the ratio of the square of a planet's orbital period is proportional to the cube of its mean distance from the Sun. If you were to express this mathematically, say for planet 1 and planet 2, you could establish some ratios. So what you would say here is that period 1 for planet 1 divided by period 2 for planet 2 squared would be equal to the semi-major axis for planet 1, S1, divided by the semi-major axis for planet 2, and then you'd cube it. So the periods squared is proportional to the ratio of the semi-major axis cubed, which is the mean distance from the Sun. You could rearrange that so that S1 cubed over T1 squared is equal to S2 cubed over T2 squared. All right? Now this comes from Newton's laws, which Kepler didn't know yet. Like I said, this ratio should be the same for all the planets. Planet 1's semi-major axis cubed divided by period squared should be the same as planet 2's. So you can see that here in this table, summarized for planetary data applied to Kepler's third law. You can look at the mean distance from the Sun for Mercury, for example, which is 57.9 times 10 to the 6 kilometers. And the period for Mercury's orbit in Earth years, 0.241 Earth years. If you take the ratio of the semi-major axis cubed to the period squared, then you'll get 3.34 times 10 to the 24 kilometers cubed per year squared. But you can see that that ratio is roughly the same for all the planets, and that's what Kepler observed in his third law. Now it's worth noting, Kepler's law here is completely descriptive. He didn't say why this was the case, he just said that it was the case, and this was based on very careful observations. But Newton came along, looked at Kepler's laws, and then derived why they were the way they were based on his universal law of gravitation. So let's do that right now. Remember, Newton's law of universal gravitation says that the force between two bodies of masses, say big M for the Sun's mass and little m for the planet mass, divided by the square of the distance between the two, the Sun and the planet, we'll call that r squared. So that's Newton's law of universal gravitation. That causes an orbit, which of course causes a centripetal force. Since the law of gravity supplies the centripetal force, we can set them equal. So if you consider the planet to be orbiting the Sun, right, then the centripetal force has to be the mass of the planet, little m, times v squared, which is its orbital speed squared, divided by r, the distance in between the planet and the Sun. We set those things equal. Now remember that the speed of the planet is equal to the planet's circumference in its orbit, right? 2 pi r, divided by the amount of time that it takes to complete an orbit, the period t. If you plug that in now for v into Newton's law of universal gravitation in the centripetal expression, our first expression above, then you can see that g big M little m over r squared equals the mass of the planet times 2 pi r over t squared, and then divided by r again. Now, doing a little bit of algebra, some of these things are going to cancel out and multiply, and then you'll end up with m 4 pi squared r over t squared equals g big M little m over r squared. Now all I have to do is cross multiply and rearrange some terms. Pause the video if you need to follow the algebra and make sure that it works for yourself. But what you'll see is that if you take the period and the radius to the left-hand side, then you end up with a period squared divided by the radius cubed. And if you take everything else over to the other side, you can see that's equal to 4 pi squared over gm, where of course g is the gravitational constant, 6.67 times 10 to the minus 11. Okay, so what that says is that for whatever planet that you've got, all right, that means that the period squared divided by the radius cubed is going to equal to some constants that don't change. In other words, big M is the mass of the sun, g is a universal constant, and of course 4 and pi squared are constants too. So for any planet that's in orbit around the sun, the period squared divided by the radius cubed is going to be equal to those constants. This is the origins of Kepler's law. You can just invert that expression, and you can say r cubed over t squared is equal to gm over 4 pi squared. Alternatively, I could have just put my stuff on the other side, and I would have ended up with the same type of expression that I had from Kepler's laws, that the ratio of the average distance from the sun cubed divided by the period squared gives me some constants for every single planet that are the same. See, that's the origins of Kepler's law. All you have to do then is realize that you can plug in the semi-major axis S for the radius. Most of them are really close to circles anyway, and you'll get the same result. So that's the derivation of Kepler's third law. So we've seen that Kepler's laws can be derived from Newton's laws. And then what happened was Newton and other astronomers noticed that there were irregularities in the planetary motion. And those irregularities should only be caused if there was another large mass next to the planet or close to the planet that was affecting its orbit. That led them to hypothesize that there were planets out there that they couldn't see, right? That were changing the orbits of the planets that they could see. And this led to the discovery of Neptune. Also, irregularities in stellar motion have led to the discovery of many planets outside of our solar system. So we look for these deviations from what we can predict, and then we look very closely for objects that might not be as bright in our sky. We turn more powerful telescopes on them and see what we can see. All right, that summarizes what I want to say about Kepler's laws for now. I'd like you to also watch this video that's done by Crash Course on the orbit of the moon to summarize some of the other sections in Chapter 5 of our textbook. As always, we're using Giancolli's Physics Principles with Applications, and I've also used some references from Sir William Jewett's textbook in this lecture, and I'd like to thank them for that. And I'll see you in class.